Welcome back to this third introductory lecture on proof techniques, where we are focusing on the proof by cases. In this second segment, we're not going to look at a specific example, we're actually going to provide a template for this proof technique. So the general form of the theorem we're going to try to prove here is like this: for all x, q of x. Now I'm always going to try and connect this with the previous example from the first segment, in which q of x was x squared plus x is even, and the domain for x was the set of all the integers. So if our goal is to prove a universally quantified statement where q of x could be anything, it doesn't even have to be a single predicate, it could be a compound proposition. How do we proceed? Well, sometimes it's kind of hard to do because there's no assumption on x other than it's a member of its universe. But in some cases, we have extra information. For example, what if you know for a fact that for any element x in the universe, it must be true that either p1 of x is true, or p2 of x is true, or ... or pn of x is true. Remember, this is the same situation we had in the previous example, where x ranged over the domain of the integers, and p1 of x was x is odd, and p2 of x was x is even. So in that case, n was equal to 2. There were only two cases. But if we knew that every integer in the domain is either odd or even, we have the expression as a fact, as a true proposition, that for all x, odd of x or even of x. When here we're just generalizing to n cases instead of 2. So if we have this additional information, and by the way, it must be the case that the domain of x here is the same universe or the same domain as for this original theorem we're trying to prove, then we can use this extra information to perform a proof by cases of the theorem. In other words, we're going to take one case assuming that p1 of x is true, and from that we're going to try to prove q of x, and then a second case where we assume that p2 of x must be true, and we try to prove q of x, and on until we assume p of n or pn of x is true, and we try to prove q of x. Because we know that for any element in the universe, at least one of these predicates must be true. We know we've covered all of the possibilities with the proof by cases. And as a side note here, notice that the disjunction we use is the regular disjunction or inclusive disjunction, meaning that it is possible that one x fall into more than one case here. But of course, the same would hold if we had used an exclusive OR here. In fact, in our previous example, an integer is either odd or even, but not both. So we had an exclusive OR in that particular example. Either way, exclusive OR or regular disjunction, this is the pattern or the conditions under which we can use the proof by cases. Now, so here is the actual template for a proof by cases under the conditions set out here. Since we're trying to prove a universal statement, we're going to start by denoting by x bar an arbitrary element of the domain or the universe. And now we can break down the proof into the n cases corresponding to this disjunction. Since we know it must be the case that for x bar, either p1 is true or p2 or ... or pn is true. So case 1 is where we have to prove that assuming p1 of x is true, we can infer, p1 of x bar is true, since now we're taking a specific but unknown element of the universe x bar. Assuming p1 of x bar, we must be able to prove q of x bar. So this subproof number 1 starts with the assumption that we need, and then proceeds to eventually prove that q of x bar holds in this case. And that concludes the first subproof. We then turn to case number 2, for which we must prove that if p2 of x bar holds, then q of x bar must also hold. Similarly, we assume to start this subproof that p2 of x bar holds, and then we go ahead through some proof to conclude that q of x bar holds again in this case. and so on and so forth through all the intermediate cases until we reach the last case, case n, for which we must prove that Pn of x bar implies Q of x bar. Again, one last time, we assume the hypothesis, namely Pn of x bar holds, and we write some proof that allows us to infer that Q of x bar holds. Now we're almost done, but not quite. All we've done is that in every possible case, Q of x holds, or Q of x bar in this case holds. So we must make sure to state that as a conclusion, that Q of x bar is true in all cases, as we just proved. And one more step that you should never forget is to generalize from x bar to the whole set of the elements in the universe using universal generalization. And this is how you prove that for all x, Q of x holds if you're using a proof by cases.